Welcome everyone. During this lecture we'll introduce the branch of physics called motion in one dimension, and we'll develop the following topics, including definitions of position, distance, and displacement. We'll introduce the topic of speed and velocity. We'll develop a position versus time graph. We'll define acceleration, and we'll also derive the one-dimensional motion with constant acceleration equations. Let's begin by discussing position, distance, and displacement. Now, before we begin, it's very useful to imagine laying a piece of masking tape on the floor. And there's my piece of masking tape. And we'll also label the masking tape in accordance with the x-axis. So there's the 0 mark, and we'll label anything to the right as positive. Anything to the left of 0 is labeled as negative. Notice also that we're specifying the locations in meter terms. Now, from this point forward, it's important to imagine that we can move around along this piece of tape, but we're not allowed to step away from it. So long as we move along this piece of tape, we are now restricting our motion to one dimension. Let's also imagine that our journey begins right here. So here we are at the beginning of the problem, and sometime later we end up at this location over here. Where we started is called our initial position, and we define it as follows. We define it as x initial, and notice that it equals -3 meters, and our final position is defined as x final, and it equals 8 meters. We're now ready to define the term position. It turns out that position is just a measure of an object's location. By laying out the masking tape as you see here, we're able to identify our location. Let's now introduce distance. Distance is a measure of a path's length between an initial and a final location. We want to also note that distance is always represented by a positive value. In other words, there's no such thing as negative distance. Let's now define something called displacement. Displacement is a measure of the shortest length between an initial and a final location. Now we have a symbol for displacement. The symbol for displacement is delta x, and in mathematics this triangle known as delta represents a change or a difference in an x value. And delta x just equals x final minus x initial. Let's now connect these principles to the diagram that we drew earlier. So for example, let's determine the distance traveled by the person shown within our first diagram. So there's the diagram that we're referring to. The person started at x equals -3 and ended their journey at x equals 8 meters. Can you tell how much distance was covered? Well, the answer is no, because we don't know the nature of the path. Now, if the person proceeded from -3 and traveled directly to the right and ended up at 8, the distance would be 11 meters. But we don't know whether the person took the direct path, or maybe the person traveled to the left initially, made a U-turn, and then proceeded to the right. Under those circumstances, the distance would be different. So the answer to the first question is cannot be determined. Without knowing the nature of the path. Let's now determine the person's displacement. Well, we have an equation for displacement. It looks like this. It looks like delta x equals x final minus x initial. And clearly this equation has no regard for the path taken between the 2 points. So if we go back to our diagram, we notice that x final is 8 meters and x initial is -3 meters. And so x final, like I said, is 8 meters minus, now x initial is equal to -3 meters, and from that our answer is 11 meters. So the person's displacement can be defined and it equals 11 meters. Let's take a look at another example now. In this example, let's imagine that the person starts their journey right here at this location. We'll label that location as x initial equals 3 meters. And the person ends their journey at this location right here, and so x final equals 6 meters. And now we'll also draw the path. So we'll imagine that the person actually starts the journey by traveling to the left like this. The person then makes a U-turn and then heads towards the right until they end up at the final location right here. We'll indicate the direction of travel with arrows, and what I'd like to find now is the total distance. Now that we have a path drawn, it is possible to determine the total distance traveled. And what we'll note is, for a while the person's traveling to the left. And what I'll do is I'll calculate the distance that the person was traveling to the left. And then for the second interval, the person was traveling to the right. We'll compute that distance as well. So we'll break this calculation into 2 parts. We'll note that the total distance equals the distance traveled to the left plus the distance traveled to the right. Now let's take a look. We started at a position of 3. We ended at a position of -5. You can see that the total distance that we traveled would be 8 meters. And if you don't see that, you can just count the distance. In other words, we started here. Here's 1, 2, 3, 4, 5, 6, 7, 8 meters that we traveled to the left. Likewise, how much distance was covered while we were traveling to the right? We started at -5. We ended at 6. If we just take the difference, in other words, 6 minus a -5, we'll discover that we traveled 11 meters to the right. You can also verify that by just counting the intervals. So if you start at -5, we're traveling 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 meters to the right. So based on this diagram, now we can determine the distance, and it happens to equal 19 meters. In part B, let's now determine the displacement. Again, we have a formula for displacement, and it looks like this. Delta x equals x final minus x initial. In this case, x final, our final location, equals 6 meters. And our initial location, right here, equals 3 meters. And so our total displacement just equals 3 meters. There are a couple observations that I'd like to share with you. First of all, a negative displacement signifies that an object's final position is located to the left of its initial position. And the second observation is distance may be determined only when the path is known. Let's now introduce the concepts of speed and velocity. Starting with the definition of average speed. Turns out that average speed is a measure of the rate at which distance is traveled with respect to time. The symbol for average speed is speed with a bar on top. Now, anytime we see a bar on top of a variable, it just means average. So we'll note that. The bar just means average. And average speed, as noted, just equals the distance divided by time. The units that we'll be using to quantify average speed are meters per second or feet per second. Let's now define the concept of instantaneous speed. An instantaneous speed is a measure of an object's speed at a specific instant in time. And the symbol for that is just speed without the line on top. And the units are the same as we had for average speed. Next, we'll define something called average velocity. And that is just a measure of an object's total displacement with respect to time. The symbol for average velocity is v, and you guessed it, there's a bar on top meaning average, and it's defined as displacement, which we earlier defined as delta x, over delta t. Now delta x could be expanded as x final minus x initial over delta t can also be expanded as t final minus t initial, and this is the equation for average velocity. Average velocity has the same units as speed and average speed, namely meters per second or feet per second. Instantaneous velocity is a measure of an object's velocity at a specific instant of time. The symbol for instantaneous velocity is just v without a bar, and the units are the same as that for speed, and average velocity. Now there are some important facts that I'd like to share with you. First of all, the magnitude of average velocity and average speed are equal when there's no change in direction. Secondly, speed is always represented by a positive value. Next, when an object is traveling to the right, its velocity is positive. And when an object is traveling to the left, its velocity is negative. We will now introduce the position versus time graph. And the process begins by utilizing the masking tape that we introduced earlier. And for this example, we'll assume that the person starts their travels at an initial position of x equals -2. So x initial equals -2 in this example. Next, the person proceeds to the far right until they reach a position of x equals 8. Next, the person reverses their direction until they reach a final position of x equals 5. We'll indicate the direction of travel by introducing arrows. We'll also mark the final location right here as x final equals 5 meters. And now I'm going to introduce some time values. So let's assume that the problem begins at an initial time of 0 seconds. Let's also assume that it took us 5 seconds to reach this location out here. So the time right here is 5 seconds. And we'll also assume that the person decided to stop at this location and take a break until a time of 12 seconds. So this is a time of 5 through 12 seconds. Next, we'll assume that the person reaches a location of 5 meters at a time of 24 seconds. So the time over here equals 24 seconds. What we'd like to do now is to graph this information on a two-dimensional graph where the vertical axis is representing x and the horizontal axis represents time. So how do we do that? Well, we mark a few points to begin with. Starting with our initial location and our initial time. Notice that at time 0, our position is -2. So that creates a dot right here. Again, the time has a value of 0, and the x value, which is vertical now, has a value of -2. The next point of interest is this one right here, and this corresponds to a position of 8. So 8 is right here at a time of 5 seconds, which of course this is a time of 5. So if we intersect those two, we find that there's a dot located right here. Now we are remaining at this location until t equals 12. So we have another point to consider, and that is a position of 8 and a time of 12. If we find that intersection, here's a time of 12, and the same position is holding. And finally, it requires 24 seconds for the entire journey. So we reach this location at a time of 24 seconds, and of course this location equals 5, so we need to find the intersection between x equals 5, which is right here, and a time of 24, which is right there. And so there is that point of intersection. And what I'll do next is just connect those dots, and by doing that we have created a position versus time graph. We will now analyze various aspects related to this journey in multiple parts. So in part A, we would like to evaluate the total distance traveled. And before we begin, I would like to call your attention to the fact that this journey has 3 distinct legs. There's this leg over here that spans a time of 0 through 5 seconds. The second leg spans a time of 5 through 12 seconds. And the third leg spans a time of 12 through 24 seconds. So the total distance